All right, we are live. All right, 1.6 is the last section in Chapter 1 that we cover in this class, and it is solving linear inequalities. I did note at the top of this page, which I didn't note in the top of your notes page, so if you pull it up digitally, you won't see this note, but this is a lot of the same material that we cover in Chapter 10, Section 1 of Math 20. A lot of you, or some of you, may not have taken Math 20 or may not have taken it with me, and that's fine. On my YouTube site, though, I do have lecture videos as well. So if you need some refresher over something that maybe we're going to go a little bit quicker on, because I'm assuming you've seen this stuff, that's a good place to go watch a slower video that will walk you more step-by-step through things if you need additional examples and things like that. So Chapter 10, Section 1 from Math 20. An inequality compares two expressions using less than, greater than, less than or equal to, or greater than or equal to symbols. Really, a linear inequality is the exact same thing as an equation, except equations have equal signs, whereas the inequalities are going to have the inequality signs. And there's one special rule, which is right here, where if you multiply or divide by a negative number, you have to flip your inequality sign. Always, always, always. Obviously, we don't have any special rules like that when it comes to equations because we don't have to worry about that. But if you multiply or divide by a negative across your inequality sign, you do have to then flip it. And when it comes to graphing, we're going to graph some of these on number lines. And you will either use parentheses or the open circle if you're using strictly less than or strictly greater than, or you will use these squared off brackets or a filled in circle if you're using less than or equal to or greater than or equal to. These are important to differentiate between, because if you're using strictly less than or strictly greater than, then what that tells you is that your endpoints are not actually included in that inequality. You can get really close to that endpoint, but you're never going to actually touch it. And so we represent that with the parentheses or the open circle. Those are your boundary points, your endpoints. Whereas the squared off brackets and the filled in circle go with the equals to aspect, because it's telling you you can actually equal those endpoints or those boundary points. I kind of like to, if it's confusing at all on the parentheses versus the brackets aspect, if you turn them sideways, a bracket can hold water. It's squared off. It's not going to run over. You can fill it up with water. Theoretically, a parenthesis, if you put some water in there, it's just going to slosh out because there's nothing to actually hold it in, which means you can't actually include that endpoint, is another way to think of it. Depends on how literal or weird you have to get with your examples. We're going to do two examples where we solve a linear inequality and graph it. I would say on your homework with the My Math Lab, most of the time they have you solve your linear inequality, and then they have you match with one of like 6 or 4 graphs that they have represented there. So you're not actually doing the graphing yourself. Are you ready to try? Solve and graph 3x minus 5 is less than 6 minus 2x. So treat this exactly like an equation. If it was an equation and it said 3x minus 5 equals 6 minus 2x, we would think about getting our x's all together and getting our constants all together and solving for our variable. We're doing the exact same thing here. I need to get all of my x's together, and I usually try to keep them positive. So I'm going to add 2x over. And if I'm moving my x's to the left, I'm going to move my constants to the right. So the opposite of negative 5 is positive 5 to move it over. I'm doing two things at once. So 3x plus 2x is 5x, which is less than 6 plus 5 is 11. Now what would I do? Divide everything by 5. So you find that x is less than 11/5. That's it. I mean, that's solving it. Now, it did say graph it, so we are going to graph it. So you might want to type in your calculator, figure out how much 11/5 is. It's 2 point something. So I know that. Again, I have to know that, like a decimal representation, to graph it on paper. Again, in the My Math Lab, you're going to pick from a listing of graphs. But if I'm going to graph it on a number line here on the paper, I need to know kind of where it falls. 3, 2, 1, 0, 1, 2, 3. So I found that x has to be less than 11/5, which is about 2 1/5. So I'm going to say 2 1/5. Sorry, what? Yeah. So I'm going to put that right. Oh, I did a filled in circle. I did this more to reference where I'm going to be at. So now the question is, if x is less than the 2.2, or this 11/5, is that lying over here on the number line or over here on the number line? Like on the left or the right of this spot? Left. So I'm going to use, since it is less than, I'm going to use a parenthesis. And it opens to the left because I am going to shade in the space to the left, because all of these values, 0, 1, 2, are less than the 2.2 or 11/5. You could do an open circle as well if you wanted to use an open circle. Again, though, the picture doesn't change. It would still head off to the left. And sometimes you're going to be asked further questions like write the value in interval notation or set builder notation. These interval and set builder notations are talked about more in the Chapter 10 section from Math 20 as well. Interval notation, though, is where you're going to use the parentheses or the brackets, which is what I kind of like doing with our graphing. We used a parenthesis here. So that tells me that that's my upper limit. So if I'm doing an interval notation, I'm going to have my upper limit is 11/5. Then what is the smallest value x can be where x is less than 11/5? Negative infinity. That's right. And anytime we do infinity, we're going to use a parenthesis because you can theoretically never get to infinity. You give me a number, I can take you one step further away, and so on. So we're always going to use parentheses. Now, I use parenthesis on that side because it's infinity. I used parenthesis on this side with the 11/5 because it was strictly less than. So this is the interval notation. Set builder notation is actually really nice when it comes to our inequalities because set builder notation is set up like this, where they will give you the x in the vertical bar, and you have to fill in this space over here. And what this says is that you have the set of x such that, and then if you've solved your inequality, you just plug in that inequality such that x is less than 11/5. This is the part that you would be responsible for typing in the My Math Lab site. It doesn't usually ask you for like all of this information, but some of the problems could. I would say more than likely the interval notation is the more common notation that is used. I know it's the one I usually use. But for the notes and things like that, I will show you both the interval notation and the set builder notation so that you get more comfortable with those. Is there any questions on how we did this? Any aspect of it, on how we solved the inequality, how we graphed the inequality, how we got the set builder, the interval notation from this inequality? Okay, let's do another one. B, we have 13 minus 7x is greater than or equal to 10x minus 4. I know I just said that I like to keep my x's positive, but I'm going to go against the grain this time because I want to show you something that happens. So I'm going to subtract my 10x to the left. Now, you don't have to. If you want to keep your x's positive and you want to add your 7x over, that's totally fine. You're going to get the same answer I'm going to get. But I want to show you what happens when we have to do that multiplying or dividing by a negative number. I'm also going to subtract my 13 over to the other side. So that I have negative 17x is greater than or equal to negative 17. To get x by itself, I would divide both sides by a negative. This is the first time, at least in this class, that you've seen we're dividing by a negative across our inequality. So we're going to have to flip our sign around. So x is less than or equal to, instead of greater than or equal to, it's less than or equal to positive 1. That's what that special rule means. Where you multiply or divide by that negative, we have to flip the sign. If x is less than or equal to positive 1, then is positive 1 my upper limit or my lower limit? Is it the biggest x can be or the smallest that x can be? Yeah, it's the largest because x has to be less than or equal to positive 1. So since this is the largest that x can be over here at 1, I'm going to use my squared off bracket and open it to the left. I'm using a squared off bracket this time because it says equal to. And when we have less than or equal to or greater than or equal to, I'm going to use my squared off brackets. And then since it's opening to the left, that means I'm headed off here towards negative infinity again. Again, you could do a filled in circle. I feel like your book uses the circles, the open circles and the negatives, or the closed circles for their graphs. But again, I really like using the brackets, even on the graphs, because now when it comes time to write my interval that x can be, it comes straight off of my graph, where my upper limit is at 1, and then I'm shooting off to negative infinity. And it comes straight down off of my graph. And there's my interval notation for this problem. And then my set builder is x such that, well, x is less than or equal to 1. Sorry, trying not to move that so much. Do we have any questions on these first two? Hopefully you'll just yell at me if you do. We also use inequalities to help us figure out the domain of different functions. Remember, the domain of a function is your inputs. It's your x values. And for most functions, your domain is negative infinity to positive infinity. But there's two possibilities, or there's two exceptions to that rule. The first exception is if x lies under a radical. And if x lies under a radical, then there's going to be some values that make that whole thing negative, and that's a problem. Because we don't want to take the square root of a negative number. So we have to limit what our x can be. It can't just be anything. The other time that you can have what I call trouble spots is if x is in the denominator. of a fraction, because we can't divide by 0, and so anything that makes that denominator go to 0 causes a problem. And so sometimes when you're finding the domain, you've got to use these inequalities in order to help you figure out what your domain can actually be for a given function. So for our first one, we have the function of f is the square root of x minus 6. Now, since it says the square root of square root and x is inside there, we can't let this x minus 6 become negative. It can be 0, but it can't be negative. So I'm going to write that as an inequality. The x minus 6, it can't be negative. So it can be greater than, or it could even be equal to 0. That means it can't be negative. And then we solve for x. We add the 6 over, so x has to be greater than or equal to 6. And as long as that is true, then what is under our radical stays positive. If x was 5, I would have 5 minus 6, which would give me a negative 1. That's the problem. And so we have to limit our domain to x being greater than or equal to 6. So how would I write this as an interval? Like, what is the smallest value that x can be? 6. And it can be 6 because we said it could be equal to. And then what is the largest value that x could be? Infinity. So this is our domain. This is the interval that our domain can lie on. If they asked it to you in Set Builder, hopefully you could write it in Set Builder. But almost always your interval is being asked for, your domain is being asked for in interval notation. So if you're just dealing with a function and the only problem spot is that you lie under an even-rooted radical, then it has to be greater than or equal to 0. That's what you got to do. If you have something where it is 1 over x, this is not one I'm going to work all the way through, but if this was our function, our problem would be that x can't equal 0. So we'd want to find out where does x equal 0, and we remove that from our domain. And we're going to see that a little bit down here. I went and picked like one of the most complicated ones you're going to see so that we can work through it together. Because for g of x, not only is x in the denominator of our fraction, but x also lies under a radical, which means it's kind of double trouble in this case. Because not only then do we want what's under our radical to be positive, but we also don't want it to be 0. Because up here, it was okay if we had 0. You can take the square root of 0. It's 0. That's not a problem. But it is a problem if it lies in the denominator of a fraction. Does anybody want to take a guess then at what our inequality is going to be for trying to find the domain of g of x? If we can't have it be 0 and we can't have it be negative.
Make it an inequality that's greater than 0?
That's exactly right. We're going to make it an inequality that's greater than 0. So this 3 minus x, if it was just the radical, and we didn't have it as part of the fraction, we would say that has to be greater than or equal to 0. But because it is in the denominator of a fraction, we have to limit it even further by saying it has to be greater than 0. Because if it equals 0, it causes a problem. So that's exactly right. So you can do it multiple different ways. Subtract the 3. Multiply by the negative 1 and flip that sign. Or you could have just moved the x over and then flip it around. So we have x is less than 3. As long as x is less than 3, then we will stay away from 0 and we stay away from negatives under our radical. So how do we write that as an interval? What kind of symbol do we use on the 3? Parenthesis. We use a parenthesis because it's strictly less than. If it has that equals to, then we do the bracket. And then set builder, we have x such that x is less than 3. Questions, questions, questions.
On that particular one, do we even worry about the x that's the numerator?
Nope. Okay. It doesn't affect our domain at all. Good question, though.
Does it always have to be 0? Like, say it would be like 3 and then equals to 1?
No, it always is 0. And the reason why is because we don't want, like, if we're just dealing with the radical, we don't want negative numbers in there. And so if we set it equal to, like, greater than or equal to 0, then we avoid all of our negative numbers. And if it's in the denominator, if we just make it strictly greater than 0, then we avoid all of the 0 aspect to that as well.
But like, you can do that greater than or equals to 1?
So that doesn't cause a trouble spot for us. We just have to really think about where the trouble happens. And the trouble is always centered around 0. Good questions. You ready to try some slightly harder inequalities? Like compound inequalities? I'm going to give you the notes kind of in 2 little pieces because I think it's helpful to have these and then also have the next bit of notes, but that's not how I wrote it in my notes. So compound inequalities are where you have 2 inequalities that are joined together by either the word and or the word or. There's really 2 different kinds of operations that we sometimes think about when it comes to joining inequalities together, and it's using the and the or. If you use and, then what you're actually talking about is the intersection of sets. If you're talking about or, then you are talking about the union of sets. We talked about unions and intersections a bit back in 1.2 at the very end of well, not even the end. Like when we were talking about finding the domain of our functions, we talked about unions and intersections. And again, if you go back and reference my video from Math 20, that's section 10 or chapter 10, section 1, it also talks about it. But here, if I can get it to slide up, is kind of a quick mini refresher about unions and intersections. Unions is where you take 2 sets, like set A and set B, and you combine them together. So they could be an or, because X can be either in set A or it could be in set B. That's union. That's what this upside or this wonky looking U. Intersection, though, is where you have to be in both. You have to be in both A and B in order to lie in that intersection. And that's what's happening when we deal with these inequalities that have and or going on. I'm going to raise that up. You'll be able to see part of a problem, but you can't see all of it. So. Again, we talked about this stuff back in 1.2, and if you want further videos, 10.1 from Math 20. We're going to do 2 examples because there's 2 different ones. We have an and one and an or one. You ready? Almost. Okay. Ready? Okay. solve and graph. This is a compound inequality. We have three different sections of this inequality. We have the -3 on the left, the inequality symbol, the middle piece, which is the 2x plus 5, and then we have another inequality symbol comparing it to 7. When they are joined up like this, what we really skipped ahead. What we really have is we have the and situation going on. What I'm saying is we have -3 is less than 2x plus 5, and the 2x plus 5 is less than or equal to 7. So when you have an and situation, and notice both of our symbols are pointed in the same direction, then we can combine them and make one complex inequality, which is actually the easiest way to approach these problems. Because when you have one complex inequality, what you're going to do is you solve it exactly like you would a regular inequality. And here's what I mean. If I cover up this less than or equal to 7, what would you do first to solve this inequality? Yeah, you'd subtract 5. And we'd subtract 5 from here, and we would subtract 5 from here. And even though it's a complex inequality, you still do the same thing. If I'm subtracting 5 from the left, the middle, I'm going to subtract 5 from the right. So you just have to do it to a third side instead of just two sides. So -3 minus 5 is -8, is less than 2x less than or equal to 7 minus 5, which is 2. Now what would I do? Yeah, divide the 2. And since I'm dividing the middle by 2, I have to divide the left by 2 and divide the right by 2. So I have -4 is less than x, which is less than or equal to 1. And I have a complex inequality right here. Now, the interval notation, or excuse me, the set builder notation is the easiest one to write because you already have it. It's the -4 is less than, not equal to, less than x, less than or equal to 1. And actually, when we're dealing with an and situation, the interval notation is really easy to come with too. Because remember, these are telling us our big limits. It's telling us how big and how small x can be. Let me show you on the graph first. 5, 4, 3, 2, 1, 0, 1, 2. Notice when I graph on paper, I usually go like 1 or 2 digits further than what my endpoints say, just so I can kind of see what's going on. Okay, if x is greater than -4, what am I doing? Look, if I'm just looking at this left part of this inequality, how do I graph that? So you're saying open circle at -4 and we're headed off this way. Correct. Because x has to be greater than -4 and we're not going to equal -4. So we're doing an open circle situation. Perfect. Now, what if x has to be less than or equal to +1? So where do these overlap? They overlap from open circle at -4 to closed circle at +1 and everything in between. Or, if you like the brackets, it's in parenthesis at -4, squared off bracket at 1, filled in. Because maybe my picture is a little deceptive. This, if I was only looking at half at a time, would go off towards like infinity, and that would go off towards infinity that way. So we're looking at where they overlap because it says and. Now from our graph, hopefully you can see the interval. The lowest that our x can be is the -4, and we're not including it. It's an open circle. the largest our x can be is at positive 1, and we do include it. Which comes straight from our complex inequality over here, our answer, our solution that we got. Negative 4 is our lower limit. The positive 1 is our upper limit. A word of caution when it comes to this on your homework and stuff. If you type in 1 comma negative 4 like this, even though you have all the right symbols, the fact that you wrote your upper limit on the left and your lower limit on the right will be incorrect. Lower limit on the left. Lower left. So put the smallest value on the left and the largest value on the right. That way you don't get that counted wrong. Questions? Okay. Let's look at an OR problem. OR will always stay split. You cannot combine these together like you can with an AND one. And that's because it's saying this 2x minus 5 is less than negative 7. So think about your number line for a second. It's less than negative 7, or the 2x plus 5, or minus 5 has to be greater than positive 1. If you think about that, just you're headed off towards the negative infinity or you're headed off towards the positive infinity. You're not actually headed off towards each other in the middle. This is an OR situation. So what do? Well, we solve each of these inequalities separately. I would add the 5, giving me 2x is less than or equal to negative 2, divide by 2. X is less than or equal to negative 1. Or do the exact same process with our other inequality. 2x is greater than 6. X is greater than 3. So let's graph this on a number line. If x has to be less than or equal to negative 1, then what am I putting at negative 1? A bracket or a parenthesis? Bracket. And if I am less than, am I going to be to the left or to the right? Left. Less is left. Okay, so I have this one graphed. Then I look at the x is greater than 3. If x is greater than 3, am I using a parenthesis or a bracket at 3? Parenthesis. To the left or to the right? Yeah, because it's got to be greater than. So there's the graph representing the information that we have. Even with a set builder, it's not any different. X such that you write down all of this inside your set builder. You can type in the word OR inside your set builder, and it's totally acceptable. You would have x is less than or equal to negative 1, or x is greater than 3. You could also do it with a comma instead of OR if you so chose. That would also be correct. But there's the set builder. It gets a tiny bit tricky when we have to do our interval, because you notice our intervals don't overlap in this case. We have two separate intervals. We have this interval on the left and this interval on the right. So how do I represent this interval on the left in interval notation? And then what about the interval on the right? Yep. So which symbol are we going to put between it? Are we going to union these, or are we going to intersect these? Yep. OR means union. If we intersected them, they have nothing in common. So there would be nothing in the intersection. We include the union, which tells us that they are joined together. Even though they have nothing in common, they are still unioned together. So you won't use your intersection symbol when you're doing your intersection problem, and that's because they overlap, and so your interval is all nice and neat. You do have to use the union symbol because you're combining two very different intervals together that have nothing in common. Are there any questions on these inequality problems that we've seen?